Thanks for coming, everyone. We're just going to jump straight into the next talk. I think we are right on time at the moment. The next speaker is Clinton Roy, who actually does a lot of really clever and interesting things, but the only thing he wanted to be introduced as is a software developer that helps make life easier for researchers. So I'll let him tell you himself about what he's doing.
Thank you, Maya. Good afternoon, everyone. My name is Clinton. I'm a software engineer. I'm currently with the Australian Synchrotron over in Melbourne. And today I'm going to talk about one of the solutions we're working on for some of our data management problems. So I'll give a brief talk about the Synchrotron. I do not have enough time to cover it in depth. There was a EuroPython talk a couple of years ago that covered that. I'll talk about HDF5, which is a file format that we're using as part of our solution. And I'll then talk about h5pydantic, which is a library we're developing to make the best use of HDF5, but also to use as an API for our scientists. So this is a lovely shot of the Australian Synchrotron. I think this was during one of our open days that we hold in between pandemics. If you're in Melbourne when they're on, come and have a look. We're a public research institute, so we welcome visitors. If we take the lid off, we are essentially a big ring where we accelerate electrons very quickly. Every time we turn those electrons at one of the corners of that circle, they release a large amount of X-rays. We take those X-rays, we filter them, we focus them, and then we fire them at samples. Each one of those different beam lines selects a different energy level of X-rays to use, and that means that they have different techniques and different sensors to be able to read what the radiation is doing to that sample. We do a lot of experiments on a lot of different types of samples. So we have chemicals we fire X-rays at, we have batteries, we have lumps of wood, we have trees, we have grains. We have fossils, we have archaeology samples of all sorts of different natures. We have paintings. We have a very wide variety of samples that we use. Storing the data and metadata about those samples is obviously just as complicated and just as varied as the number of samples we've got. A lot of our users like to do things to the samples while they're firing X-rays at them. They like to put the samples under strain. They like to heat them up, cool them down, apply shearing forces, apply a magnetic field, apply a radio field, apply UV light to them, apply different chemicals to them, apply pressure to them. Again, a really wide variety of things that our users like to do to their samples. For a particular experiment, we want to record exactly the energy level of X-rays that we're putting into the sample. We often want to record how far our sample is from one of our X-ray sensors or detectors. A lot of our X-ray detectors, they look like cameras essentially, but each one of the pixels, instead of seeing a pixel of light, sees an X-ray particle. So the images that we get out of them, they often can be thought of very much like a camera image. And much like a camera image, you want to record things like your exposure time for that image. We're doing experiments. The real world is very noisy. That means that all of our sensors on our experiments, they're not always going to measure everything perfectly. So what you want to do in an experiment is, before you start your experiment, you've got your apparatus set up. You want to take a lot of measurements that just measure your background noise, your background radiation, and you want to figure out how sensitive your sensors are at that point in time. So you might want to run your experiment, but with no X-rays going through, just to work out if your sensors are accidentally detecting X-rays when there are no X-rays. Or maybe there's a solar storm at that point in time, so you've got some external radiation giving you some background noise. And there's other calibration data, like exactly where the X-ray is firing, because you might need to go and do some trigonometry later on to help you work out where your X-rays have been coming from, if you know where they've been hitting. Once you've got a lot of raw, noisy, messy data, and you've got your calibration data, then you're going to probably want to do some stats on it. And when you're doing statistical work, you come into it with an algorithm, plus there's normally quite a few fitting parameters where you'll take an average of something, or you'll take a window of something, and you get to play with that statistical work. You can try to run those same algorithms with different fitting arguments to see the best outcome. And you really want to record all of those arguments that you're using for your statistical work, so that later on when you publish a paper, you can let other people repeat the work. So what I really want to get through with this slide is to say that for every experiment that we're doing at the Synchrotron, there are thousands, tens of thousands of pieces of data that we want to record. And the way that a lot of this stuff works, it takes a long time for people to be able to get permission to come and do an experiment. They collect a lot of data, and then it might take them months to do the statistical analysis. So they might not get to look at this data for like 6, 12 months later. So what we really want to do is organize all of this data, annotate it in such a way that in 12 months' time when they pick it up, it's not just a number, but it's some documentation around the number that shows them exactly what that number meant 12 months ago when they did the experiment. What our users want, ideally, is they want to bring a sample on site, do an experiment on that sample, and that can be a dozen or so different experiments on that one sample. And then they want to take away a file or maybe a dozen files about their experiment with all of their data and all of their metadata in one lump. Ideally, that's all in one file, but if we can get close to one file, that's good enough for us. One file format that lets us get fairly close to that ideal is HDF5. It stands for hierarchical data format. We'll explain the hierarchical bit fairly quickly. You can think of HDF5s as an archive file format, so like a tarball or a zip file. It's one file, but inside it, it contains, or you can think of it as containing a directory listing of other files. So it's got lots of other files in it, or it's got a little file system inside of it. There are only 3 concepts that we're going to concentrate on with HDF5 today, and this does cover the bulk of our use cases. We have groups in HDF5 files. These are your directories or folders, depending on which operating systems you're comfortable with. You can have nested groups, and indeed, the way that HDF5 talks about them, they are compatible with POSIX naming conventions. So they very much look like directories inside the HDF5 file. We have datasets. Datasets are multi-dimensional arrays. You can have as many dimensions as you want. It's very common for us at the Synchrotron, where we have a detector, an X-ray detector that's taking images of X-ray particles to store that image as a 2D array, and that would go into a dataset into our HDF5 file. And the third concept are attributes. Attributes are key value metadata pieces. They can be thought of as tags that you can tag onto groups and datasets. So you can sort of see where attributes will be really useful, because we can divide up our HDF5 file into our 4 groups, where we've got our sample data, we've got our calibration data, we've got our statistical data. So we can have a different group for those. And all of the images that we're detecting off our sensors, we can use datasets for those. And all of that metadata of those particular numbers that we were picking, we can use attributes to store those. So if we were to do a little bit of a hand wavy contents of a HDF5 file for part of an experiment. Here we've got a sample, a top-level sample group, a top-level beam group, a top-level calibration group, and a top-level processing group. The calibration group has a subgroup there, like a nested group, a position group. You can see at calibration no beam, we have a data set. So you can just pretend that's a long array there. Just showing you a little bit there. So that's our calibration shot where we've got no X-ray beams. So in an ideal world, we would hope that we would not pick up any X-rays and that would be all zero, but I've put a couple of ones in there just to indicate that it's a calibration measurement. So the reason we do it is because we know it won't always be zeros. And you can see all of the lines that we've got equal signs in there. Those are our attribute examples. So we've got things like sample thickness and sample concentration attributes of the sample group. Going to introduce now one of the libraries that we use called h5py. It's a Python library that does all of the low-level HDF5 file manipulation for us. If we just concentrate on the calibration group, we'll just show the code for writing that out now. So h5py has a file concept. You open up the file in write mode, very similar to the standard Python file. We create a group within that file called calibration. And within that calibration group, we create a data set and we pass along our X-ray sensor image, which is our array of numbers there. Down the bottom, we have the calibration group inside position, and we can see the attributes tagged onto the position group. And the way that h5py makes that available is through a Python dictionary. So key value pairs of data that we're interested in. So if we were writing out a HDF5 file to cover the calibration of our example experiment, that's how we would do it. The h5py API, it's very straightforward. It's really well mapped from the core concepts to the core code that you'd want to write. The problem there, though, is that if you do that for all of the sample data that you've got, you will end up writing a lot of code to do a lot of data manipulation, and a lot of that code can be generated for you. So in h5pydantic, what we're trying to do there is combine h5py to do a lot of the low-level HDF5 file manipulation with high-level concepts coming from Pydantic. So Pydantic lets you create models in Python. It helps you do a lot of validation work, which is actually really important for us with HDF5 files, as we'll come on to. So we've got the three core concepts of HDF5 files: a group, a dataset, and attributes. When we map those to Pydantic, we create a model for a group, a model for a dataset, and fields of models can be used as attributes. So we'll go on to an example of that now. So here is our first introduction of the h5pydantic model. The h5 group and the h5 dataset, they are Pydantic models. So everything that you can do with Pydantic, you can do with h5 group and h5 dataset. And we'll get back to that in a little bit later. h5 integer is a data type. HDF5 files are very specific about the data types that you store. And I am very particular about being able to validate all of the data entries that you're giving us in the models. And we'll get back to that a little bit later on. One slight disadvantage with Python is that it is a single pass language. You have to declare something before you use it. So you actually kind of have to read these models from the bottom up. in this example. So right down the bottom, we've got an experiment. It's got a calibration field, which goes up to the previous class, which is calibration. That calibration has a no beam calibration image field and a position field. And we go up again. Our calibration image class is a data set. So this is an array. And here we declare the data type of it. So each individual bit in the array is a h5 integer, 32 bits. And the shape of the array is a 3x2 array. So it's a very small example sensor. And then right at the top, we've got our position, where we've just got the X and Y fields. Those are attributes, and they're both 32-bit integers. So essentially, we are declaring the data structures that we want in our HDF5 files. We don't have any h5py code there. All of the code to create the groups, create the data sets, store the attributes, that's done in the background by the h5pydantic classes h5 group and h5 dataset. So in a database world, if you are making a website with a relational backend, you would use an object relation mapper, or a lot of people would use an object relation mapper. h5pydantic can be thought of as a object relation mapper, but instead of mapping to a relational database, it maps to a HDF5 file. So if we were to use that model now on one of our experiments, we would instantiate the experiment. We'd pass in all of the metadata as dictionaries there. And the important point here is that because they're Pydantic classes, Pydantic will make sure that the names, position, X and Y are all correctly spelt. If anything's missing, Pydantic will complain. It will also make sure that the types, so the integers 247 and 253, it'll make sure that the types of all of the values that we're passing along will validate as well. Separately, we pass along the calibration data to no beam. And we do that because it's very common for us to have a lot of metadata, and our images are generally on a file, so we want to load those up separately and add them on. And then we would call the dump call, and that dumps this Pydantic model that we've instantiated, we've given it values, then we dump that to our experiment.hdf5 file. So the advantage for the scientist here is they've been able to run their experiments, add in all of the data and metadata for their experiments, dump it to a HDF5 file, and they've not had to think about any h5py code. All of the marshalling has been handled for them in the background, but almost more importantly, all of the fields that are required, Pydantic will check that anything that's been declared as being required, Pydantic will make sure it's been passed, and it will check all of the values match the data types. Later on, like 12 months later on, our user goes to load up the data. They can import their experiment model. They can load from the same file, and then they can just grab the attributes from experiment calibration position X and experiment calibration position Y. So again, they've got all of the data from their experiments. They haven't had to do any HDF5 parsing. Like the only reason they sort of know that there's HDF5 in the background is because of the suffix on the end of the file. So we're letting the scientists, we're letting the scientists declare these classes so that they can get on with running their experiments, and we're letting them analyze the data later on without having to drag us software engineers in. So we're getting out of their way, or trying to get out of their way. Everything that we do in h5pydantic, it is still a Pydantic model. So all the features of Pydantic are still available to you. You don't have to just declare a model with a type in a field. You can add in as much metadata as you want into that field. For us, we'd be really interested in adding documentation, units, and relationships between fields. So if we go back and have a look at declaring our beam group, which has a little bit more metadata and descriptive power describing our setup, we've got the energy describing the energy of the X-rays that we're using to hit the sample. The Pydantic field there, we passed along the GE equals 0, so that's greater than or equal to 0. So we always have to pass along a positive number for our X-ray field strength. We can document it. We can say that instead of just beam.energy, it's actually the X-ray beam energy. And we can pass along a unit using the pint module, which is one of the libraries that you can use to declare that your numbers have real-world physical units associated with them. And similarly with the distance, we can declare that as a field, our distance from our sample to our detector, it has to be at least 0, can't be a negative distance. And that's all we have to do. Pydantic will check that for us. And we measure that in millimeters. So this is where we start seeing the advantage of declaring these models like this, is that we can put all of that extra semantic knowledge around these small names like energy and distance. We can add as much documentation as we want here. I've used short sentences here so that I can fit them on the slide, but we can shove as much documentation in there as we need, so that in 2 or 3 years' time, we pick up your HDF5 data and it's not just full of numbers. All of this documentation is in your data file so that you can see the number and then you can see the documentation and know exactly what it is. And there's a lot of software that gets used in a lot of different contexts. So different beams, they have different techniques that different beam lines have different techniques that they use for doing experiments. And there's lots of different software for doing the analysis work after the fact. So one of the things that we want to do is provide non-programmer documentation describing the HDF5 format. So using Sphinx, we can at the moment generate a PDF file describing all of the attributes, all of the groups, and all of the metadata in the HDF5 file in a straight PDF file, and it doesn't have to mention any Python stuff at all. So if you want to take your HDF5 file and go and do some analysis work in MATLAB, for example, we can generate a document that tells you how the file is laid out, and you don't need to learn Python at all. One of the other things that we can start doing is we can use some of the features of Pydantic to start doing versioning. So we have a set of classes. We can add a version number to that set of classes that describes our HDF5 file. When we dump that HDF5 file, we can store that version in the file. Later on, a year later, 2 years later, when we're reading that file up, if the model has advanced, we can check the versions and we can make sure that if there are parts of the file that we don't know how to parse, we can actually have a warning about that. And we can do migration work as well. So again, that's all using features that are built into Pydantic and other libraries that are built around Pydantic. We are leveraging those. We're not writing all of that from scratch. So the overall design goals of h5pydantic, we have 3 main aims. We want to make it such that if you can instantiate a h5pydantic model, feed it data, feed it metadata, you should be able to save that file to disk. The only problem that we want you to be having is if you run out of disk space. It's quite easy with h5py to generate a Python object, ask h5py to save it to a HDF5 file, and for h5py to bail out at you and saying, I don't know how to store this Python object. We don't want that happening with h5pydantic, so we add validators to everything to make sure that once you've instantiated a model, you can save it to a disk. Because the very last thing that we want is to run an experiment, create a model, get all of this metadata, and then at the last minute, when we attempt to save it to disk, it fails because we haven't got a bit of validation right. And that's definitely a thing that can happen with h5py. We want to expose all HDF5 features. Today I've shown you the core concepts that you need to save and load data. There are a lot of extra features that you can do. So for example, you can add different compression algorithms to different parts of your file. So if you've got like some of our beamlines that are going to have 2 or 3 different detectors, they will generate very large arrays, and some of those arrays will have lots of zeros, so they'll compress easily with this type of compression. Some of our other detectors won't have a lot of zeros, and they'll be best off being compressed with a different algorithm. So I want to make sure that we can expose all HDF5 features with h5pydantic, and you can declare that stuff, and you don't have to do a lot of handwritten code for that. And similarly, I want to make sure that all Pydantic features can be used. I don't want to block anyone off from using h5pydantic and that they only have to use our API for declaring things. They're still Pydantic classes, and you should be able to use all the Pydantic features that you want.
Thanks. All right. I see we already have a question. Yes, go on.
Sorry. I have like 3 questions. I'm going to try and mush them together to pretend it's like one.
Can we have one question?
Okay. I don't know much about plasma physics. I'm inferring that HD5 is like a shot. What I do know is that that's a very, very big bit of data that is received in those experiment shots. So my question is, performance V2. Pydantic V2 or V1?
So some of our beamline software. So we are building on a third-party open source software toolkit to run the high-level experiments at the Synchrotron. That's called Blue Sky. They use a lot of Pydantic models, and at the moment they're mostly using V1. So we're constrained from being able to use V2 yet. If it's very likely that individual shots that we're taking are not going to be very large. Over the course of an experiment, like half an hour, if we're taking a shot every 20 seconds or something like that, the overall file might get very large, but individual shots won't get large.
But performance bottlenecks are not a thing?
Yeah, so I'm not at all concerned about performance. That might come to bite me in the tush later on.
No, but the big difference between V1 and V2, that was all.
Yeah, I don't see that it's a huge problem for us. We are doing a lot of hardware work, and that's where the slow things are going to happen.
Very good, thank you.
Thank you. I encourage you to corner Roy, Mr. Roy later. Clinton, I guess we'll call you Clinton. Is that your name? Is that really your name? Any other questions? There's one over there, yep.
Hi. I was just wondering, you mentioned when introducing HDF5 files sort of a concept of an LRM, talking to a relational database. Some of those tools can inspect a database and spit out, say, a suggested model. Is it possible to do the same with this and an existing H5 file that may have been created by a scientist and you're sort of given it later on and don't know much about it? Can you inspect it and generate the Pydantic models, or could it give you some suggestions?
We can give it a burl, but it's definitely not a use case that we've thought about. So for us, the HDF5 file format is mostly going to be internal and like a marshalling format rather than a final product format. So for most of the files that we're dealing with, they're going to be created internally. So we're going to have some creation control over it so that we're not having to reverse engineer that.
Yep.
Having said that, we can give it a whirl.
Okay, thanks.
Thank you. I think we'll stop there. Clinton, I have a mug for you as the traditional thank you
Thank you
for
very much.
speakers. Please, everyone, thank you.